on Root of Trust and Digital Identity. Today's webinar is hosted by WiseKey, a signatory of the Cybersecurity Tech Accord, and a global cybersecurity company that deploys large-scale digital identity ecosystems for people and objects using blockchain, AI, and IoT. Last year, the Tech Accord announced a new partnership with the Global Forum on Cyber Expertise to strengthen cyber capacity building through the exchange of best practices. To further our commitment under that umbrella, we launched a series of webinars to help increase the understanding of key cybersecurity topics, such as the one you will hear today. Today's webinar is presented by James Livingston, VP of Sales and Business Development at WiseKey, where he brings over 20 years of experience in sales, marketing, and business development for semiconductors, software, and cybersecurity services. He's also joined by his colleagues Steve and Pedro. We welcome you to share questions using the chat box located on the right side of your screen, as there will be time at the end of the presentation to address questions. And now I'll turn it over to James.
Thank you very much. It's always good to get up and running on time. Also understanding that some people take a little bit of time to get systems up and running. I will kind of just get started in this, the upfront part of it, covering some market trends, and then we'll get into the details. So people dialing in right now, you can kind of ease your way into this webinar. First thing that I wanted to talk about was just a few cybersecurity market trends, just to get a framework for why the concept of digital identities and security is important. I don't want to preach to the choir on this, but I do want to raise some just major trends that are pushing the importance of digital identities. The first digital trend is this concept of the IoT race, where every single sector that has electronics involved in it is racing to digitize. And even sectors that don't have electronics involved are racing to move into a digital strategy. So they're doing this to connect things. And it's not just the connection of the things, but really important to that is the collection of data from those things. Some of those things are getting connected to add user conveniences, new features. A lot of those things that are getting connected are actually to collect data for the original manufacturers or for cloud-based services. So there's this huge race to connect everything from your coffee pot to your bathroom scale. All of these different devices are connecting, and at a huge rate. I won't go through all of the 20 billion, 30 billion, 50 billion connected devices by 2020, because the numbers actually are just all over the place. And the real, I think it was put really well in one place, which is everything that will benefit from being connected to the internet will be connected. So regardless of the numbers, everything that will benefit will connect at some point. The other market trend right now is this state of insecurity. So while all of these vendors are racing to digitize and connect their products, it's kind of this gold rush theory where everybody's just setting up stakes and building small little camps, and they're just mining for this gold rush time right now. And under these types of circumstances, functionality is the main focus. How do I connect my product? The security takes the backseat. And using that gold rush analogy, it really is, I don't care about the security of my, what's inside of my tent. I just want to get close enough to the river so that I can pan for gold. I'll worry about security, like building a house and putting a vault and all of those things later. But right now, I just got to get in on this gold rush. Another cybersecurity market trend that is driving a need and a focus on digital identities and security is the illicit trade and counterfeit market. Numbers here estimating $4.2 trillion lost to anti-counterfeiting and piracy by 2022. And that's lost revenues for companies. And as a result, when the companies lose revenue, there's also the butterfly effect now, where you're talking about jobs that are lost. So if a company's losing money to a counterfeiting scheme, to this channel, to this stream, they're losing revenues. That means they cut jobs. So the estimate here is 5.4 million legitimate jobs are at risk due to piracy and counterfeiting. So with some of these trends as the backdrop for why digital identity and the security of digital identities and certificates and root of trust, moving into this space, this kind of layout of the threats are everywhere. So from the left-hand side, you have your sensors and smart objects. In the middle, you have the gateways and routers that connect them to the cloud or IoT platforms. And all the way through to the applications and the smartphones, the tablets, the PCs, all the connected devices that are connecting on the other side for the applications. So across this whole wide landscape, there's all of these attacks where people can enter to take control of devices, insert non-authorized devices, penetrating the network through these low security, higher risk, higher footprint objects. Then you move into the gateways and the routers, and there's the opportunity to intercept and redirect data or broadcast fake content. Up into the IoT platforms, accessing private data that's being stored there, disrupting service, knocking out entire grids of interconnectivity, and then manipulating or controlling decisions. So if you can get to the application side, you can actually make a decision on a power plant, whether it should cool itself down or heat itself up. That's large scale, or even just intercepting and controlling autonomous vehicles, things like that. There's this entire landscape. And the good news is that in the center, the gateways, routers, IoT platforms, that's a lot of traditional IT security, and a lot of time and money has been spent there. But that's been kind of focused on a centralized security platform. Now, as we decentralize and push all of this decision-making out into these edge products and these smartphones and tablets, there's a new focus that needs to shift from the old school paradigm into a new school paradigm. And I'll talk about that a little bit later. But moving into the defense here against the attacks, it's very important for these edge devices that there's an immutable identity. So that's the ability to identify and authenticate these edge devices all the way through this entire landscape. So if you give them the ability to identify themselves and then match that to certificates that gives them roles and permissions and attests to that identity, with those two components connected, you can create a secure end-to-end connection all the way through, from smart objects all the way through to the application. This is where we get into the topic of today's conversation, about the identities, the certificates, and how you build that infrastructure. With that, I will take a quick marketing advertisement break here and say, WiseKey company overview, who are we? We're a global leader in the delivery of integrated security products, focusing on the Internet of Things and digital identity ecosystem. Been around since 1999, about 120 employees worldwide, headquarters out of Geneva. And with this 20 years of experience inside of the digital security space, we have focused on the protection of users, devices, data, and all of transactions that are happening in the connected world. The markets that we focus those energies and experience into is secured IoT, brand protection, and trust protocols. Those are the markets where we go in secured IoT, where we're building access controls, connected devices, brand protection. We start moving into anti-counterfeiting, printer cartridge protection, things like that. And then also trust protocols. Since we have this 20 years of experience, we can branch that into leveraging blockchain, artificial intelligence, and moving into those trust protocol platforms that become services and platforms that people can use. So that's the kind of who we are, why we're speaking on this topic. What we have done as a company is focused on 3 pillars for our platform. First is a secure trust anchor. That's the root of trust. We'll get into what a root of trust looks like further down. We use our hardware, which is microchips, typically referred to as secure elements. So we take secured hardware to protect connected devices and the data that they're generating. And we match and merge that together with trusted provisioning and management of digital identities and certificates in our software platforms. So if you can put all three of those things together, you can actually create an end-to-end secure connection for our customers' devices, employees, individuals, all the way across the board. So getting into the topic of today's webinar, which is digital identities. So we've broken this down into three categories, which we refer to as connected trust essentials. First category is digital identities, which is just a unique online identity for an individual, an organization, or an electronic device. We'll break that down. The root of trust, which has a couple of, root of trust is a very big term, but we'll break it down into a couple of categories, easier to understand. So the root of trust is just a source that can always be trusted within a cryptographic system. So that's your bedrock, that's your base root that you can trust for all of the rest of the security functions to operate. And then PKI, or public key infrastructure, which is referred to as kind of a set of rules, policies, and procedures needed to create and manage and the use of digital certificates. So we'll cover all three of these in a little bit more detail. And really the intention of this level of presentation was to really be more informational, top level, so that you can get an idea of what these components are and concepts are. We'd be happy to deep dive with anybody that wants to get into the bits and bytes of this, but this is really meant to kind of stay high level. So digital identities. Digital identity, just reading straight from the quote, refers to the set of digital information that's associated with a particular individual. So for people, things like user IDs, passwords, access control lists, public key certificates, voice print patterns, these are all of a collection of digital information that can be used to prove the identity of an individual. And I'm going to run through a couple of examples, and I'm going to start off with the kind of a real easy, simple example of an identity and how we use that to accomplish something. So if we take Jane here on the side, Jane has a business trip to Paris. She needs to figure out how to get through the approval process to do that. First of all, Jane has a unique identifier. It's her fingerprint. You use that fingerprint at some point along the line, along with some other credentials, to get a passport. So that passport was given to her by an accredited an agency. So that passport then collected various pieces of information to prove and attest that Jane is who she says she is. She presents that passport to the TSA agent. That's a positive identification. And this whole process has been, even though it's using some digital components nowadays because the passport's scanned, it's still using a human-to-human interaction. So Jane has shown her passport to the TSA agent. He looks at her, looks at all of the information, says you're good to go, board your plane. There's some other examples. Say this guy Tony here wants to get into a ultra secure level in his building, but he's not going to go through a security guard. He's going to go through a machine. So Tony might use facial recognition here with the machine. His credential might be an employee badge that has a set of roles and permissions associated with it, so that Tony can prove that he's Tony and that he has something, his credential here, and the access control system here can validate and authenticate Tony and also the roles that he has, which floors are available to him. That was a human to machine. The growing landscape of IoT presents this new type of authentication and permissions, which is machine to machine. So we have over here Mr. Thermostat, and Mr. Stat would like to just connect to the cloud to get an update to his software. What does he use as a unique identifier? He was born with a unique ID and a private key. Now, he might not have been born with both, but he might have acquired one along the way, stored one, created one. More and more of these type of devices will be born at the factory, or even the silicon used in them will be born with this type of a unique identifier. This is the digital ID that we talk about. With that digital ID, a digital certificate can be created to attest to that thermostat's identity and also the connectivity and the roles. Then with cloud registration through the original equipment manufacturer or through the service provider that is being used, there might be some human intervention there where maybe a username and a password, but after that's set up, that thermostat has the ability to connect to the cloud, ask for updates to software, ask for control functionality for its user from another location, and do the things that we look at these other human cases. They're trying to get to somewhere and accomplish something. This is the machine-to-machine example. So with that in mind, looking at this machine-to-machine, this identity of this machine becomes very important. This is where we talk about identity as the new perimeter. And this is where I was talking about the old paradigm of centralized security for digital information was the use of IT networks protected by a firewall. So everything inside of the firewall, you used a VPN into your network, and then you were inside of the network, or when you plug in your LAN connection inside of your network, you are safe inside of your firewall security. So the threats have to attack at that firewall perimeter. The change with these connected devices is that now identity-defined security is what this IoT landscape is moving towards, where instead of everything being inside of one closed firewall, the users at the center are now using all of these different devices. That identity needs to be used as the perimeter, so the ability to authenticate and identify each one of these devices to a user, to an application, or to an organization. And therefore, this identity perimeter is what has to be created first and then protected. So that's just kind of the paradigm shift from the centralized firewall type of IT network security into this big landscape of IoT security. So that was a basic overview of digital identities. We're going to talk a little bit about root of trust. Root of trust, I like the lock and key example. I trust that my front door is locked because I put my key in it, I turned it, and I have the key in my pocket. I don't give the key to anyone else. If I do, then I've changed my chain of trust a little bit. Now I have to trust two people. If it's just in my pocket and I know that the door was shut and I locked it, then I have trust in there. But if I lose that key, I no longer have trust that my door is locked and my house is safe. So that's the general idea of protection and lock from this key concept. So the root of trust, or like I said earlier, is kind of this umbrella term that can benefit from some narrowing. We're going to break it up into two categories: the hardware root of trust, which is an anchor of an IoT device security chain, and the transactional root of trust, which deals with the certificates and identities and permissions of these IoT devices. So if we look at a hardware root of trust, and this comes from our long experience in the secure element side of the business. So the hardware root of trust for an IoT device protects the private identities, the private key, establishes a chain of trust for the device, and preserves the integrity of the firmware and the data. So a microprocessor, if we just break down an IoT device into very two basic blocks, you have your processing unit, your computational unit. That's where your applications, your wireless connectivity, your memory, and your boot ROM sit. The security component for the hardware root of trust comes from a standalone secure element that stores and protects the keys, the secrets, the signature, certificates, and it does so inside of a tamper-resistant, tamper-evident package. That piece of silicon there is designed solely to be a vault for secure information, where the microprocessor is not designed that way. You can add some software security functions to it to isolate some of the memory blocks, do things like that. But ultimately, the microprocessor, by its core nature, is meant to be open because it's got the connectivity, it's got the general purpose processing, it's got input, output, things like that. Whereas the secure element is designed not to connect to the outside world. It's meant to secure and protect secrets and communicate in a protected channel between the microprocessor. So this is when we talk about a hardware root of trust. This is the basic type of hardware that we're talking about. The other side of root of trust is a larger concept, which is transactional root of trust. So if we look at an IoT landscape again, you have the devices on the left side, you have an IoT platform in the middle, and then you have your applications on the other side. So this transactional root of trust establishes the cryptographic operations, including the digital certificates, the signatures, the firmware, and messages, and protects them and creates those certificates on the IoT side, on the device side. And then as you roll through the IoT platform, you have connectivity, you have decision-making, you have AI, video and data analytics, these different blocks that in order to perform their functions need to be able to authenticate and identify the IoT device, and then also confirm that that device is connecting to the right applications with the right roles and permissions. So the transactional root of trust helps for this whole connected ecosystem to create trust. So create secure connections between the gateways, the devices, the applications, and the platforms, and then also protect the data as it travels through this entire ecosystem. That kind of creates the concept of what we're talking about, classes of data. So in order for that IoT platform to perform those functions that we were talking about, it has to trust the information. It has to trust the device. Very low-end, non-trusted devices connect all the time. A device identity isn't even known, or maybe it's a pre-existing username password that was already set up for the device. So the network security is low. Data integrity can't be validated, which means I can't really trust the data. I might connect to the device, but I might not be able to do anything with the data. You'd be surprised at how many connected devices fall into this untrusted data category. And this is a major, major concern. This is where botnet attacks and things like that happen, where you don't have a trusted, authenticated device identity. The second class of data is device data, where we can at least trust the device. So the device has an identity, that's great. Network security is increasing, but I still can't validate the data integrity. So I know the device, but I haven't validated or made sure that the data can be trusted. So the next level, the highest level here on this oversimplified case here is smart data. That's where the device identity is known, network security has been proven, and the data integrity is validated. So not only have I authenticated the device, I have authenticated and validated the data. This is where smart decisions can be made. So I've moved to decision making with maybe a human involved to fully autonomous decisions being made between the device, the platform, and the applications. So this right-hand smart data class is the goal of this whole IoT space. There's a lot of work still left to get here, but this is kind of where we're all trying to head towards. So that was digital identities, a little bit about root of trust. Break now into public key infrastructure. So to split this up, make it a little bit easier, we're going to talk about public keys and the infrastructure. So we'll break this up into two parts: public and private key pairs, unique identities, the use of them for sign and verifying, and then we'll talk about a little bit about the infrastructure and what that layout looks like. So let's talk about a private key. So private keys are unique. Like we talked about earlier, they are a connected device's private validated identity can be derived from this private key. Or a combination of a unique ID plus a private key can get you to a certificate. But the important thing about a private key is unique. It's only known to the owner. And in some cases, that owner is just the device. The user of it never even knows that private key. Just the device itself knows its own private key. And it's used for the signing side of a digital signature algorithm or DSA function. The public key is used to verify that signature. So it's got, along with some original data, the public key and a signature, we can use that publicly to verify. So up here in the right-hand corner, a private key and a public key have this mathematical relationship. So the public key contains information that can prove it knows what the private key is without ever exposing the private key. So private key stays secure. Public key is used for public verification. So say you have some data, you want to verify it, you can sign that data with your private key or the object's private key, take it through the DSA sign process, you get a public signature. How do you verify it? Take the data plus that public key that has that unique mathematical relationship to the private key, the public signature, run it through the verification process, out comes your validated signature. So, like I mentioned at the very beginning of this, very oversimplified. There's a lot of very complex cryptography that goes into this, but the good news is it's very complex and it's also standardized. So companies like WiseKey that use industry-based standards for the cryptographic functions allow for secure connection across open platforms like IoT platforms. Take an Azure or an AWS or all of those platforms out there. They rely on standards-based cryptography. We specialize in understanding how to implement that standards-based cryptography very well. So that's the public-private key, oversimplified, but hopefully easy to understand. Let's talk about certificates and root of trust. So a root CA represents a trust anchor. So this is the, like I said before, this is kind of the bedrock of this transactional root of trust. So by trusting the signatures coming from a root certificate authority, it's possible then to build this chain of trust that rolls through the entire ecosystem. So you have a root CA, you have a public key, a public signature, a private key. That root CA can then either self-sign a certificate and use that out in the ecosystem, or it can sign an intermediate CA's certificate. And multiple intermediate CAs can be created from there, 1, 2, 3, N, created from that root CA. And then you have your end identity. So that intermediate CA can then sign the end entity certificate. What you end up with, just one example here, is a certified unique identity. So you take the certificate data here is examples of version, a serial number, the validity period, issuing name, usage extensions. So with that public signature, that public key, that certified unique identity can be used across the entire ecosystem to prove the identity of a device and attest to the roles that it can perform. So with all of these components that we've talked about, digital identities, creating a unique ID for a device, protecting that unique ID and that unique identity and that private key on that device, you can create secure connections. Adding certificates then allows you to connect and communicate through the entire IoT landscape. You've created now a digitally verifiable and authenticated device. It's secure through the IoT platform out to the applications. What have you done? You've created the opportunity to get into areas like eliminating illicit trade. So trusted identities and certificates can start the root of a distributed ledger. So blockchain, typical distributed ledger technology, has to start from a trusted identity. It has to start from somewhere where the root of this whole blockchain was trusted at the beginning. And so it's been authenticated, it's been verified, and now you create this immutable trust all the way through the supply chain. So if you can start to add authenticated identities to pharmaceuticals, to drugs, to sporting goods, to high-end luxury watches, things like that, you can eliminate this counterfeit and illicit trade market that we talked about at the beginning. Just huge dollars here. It's important for the distributed ledger to be able to trust it from the beginning, so that each step along the way in the entire supply chain can be tracked back to where did it break? If there's an issue with counterfeit drug getting in the market, can I track this back to the point where was it the manufacturer, the distributor, the point of sale? And that distributed ledger technology will allow you to track it back through the steps. You also enter into some new digital spaces like connected consumers. So NFC-enabled chips enable strong authentication of genuine goods. We've seen this in kind of starting to grow in that higher-end luxury brand space, where high-end handbags, watches, very expensive spirits, where you want to authenticate and validate that you're buying a genuine product. So that's moving into the digital landscape. It's also growing into even not the highest end of goods, but the mid-range or available to everybody. The space where connecting the device connects it to the brand name. So you connect a jersey, and now you can authenticate it, and you can also connect with the brand owner's connected platform. So you can get VIP access to tickets and information. Trusting this connected consumer data is very important. So again, if you don't have smart data here, you just have connected data, the OEM brands can't make the decision on what they're doing for the next jersey to build, because that data, they can't trust that it's coming from real users, authentic jerseys. And in this space, where they get to smart data, that's where they can make decisions now on, say, a geographic ad campaign or a user-based product that they want to build next based on the information that they've collected. So connecting consumers starts as a way to connect the brands, and then the brands collect data, and then the brands create their next generation of products. The last category on here is autonomous safety. So with the push of autonomous decisions being made between machines, I use the example of a thermostat connecting to the cloud. Not a big risk factor there. Maybe if somebody hacks in and controls your Nest thermostat at your house, might be inconvenient. They're probably not going to get really valuable data. But if you think about it from a machine-to-machine connectivity, like an autonomous car to another autonomous car, or to a traffic signal, or to an access control system, then this is where you start to get worried about safety. So it's not just convenience, but where these decisions are being made out at the very edge for a braking system to decide to brake in time to avoid a collision, that needs to be smart data. You need to trust that data, and you also need to secure that connection. And this is where the value of leveraging trusted data can move into artificial intelligence and allow these decisions to be made at the edge. And with that, I think I've kind of ran right through this presentation, leaving plenty of time for any Q&A on this general topic of digital identities, certificates, root of trust. So I would open this up now.
So James, thanks for sharing. I just have a couple questions. It doesn't look like anyone's entered anything in the chat box yet, but if you do have questions, please feel free to use the chat box. My first question is, are the private keys ever exchanged between public parties?
It's a good question, and it's a little confusing. The private keys themselves are always secured on the device. They are never used publicly. There's some confusion sometimes about how are the private keys inserted into the devices. There's the concept of a HSM, hardware security module, which can generate a private key and store it into that device. That's the only time where a private key is outside of the device before it's birth, before it's out there and installed. And in that case, all of the security parameters are taken between the HSM and the device to generate the secure private key and store it inside of the device. After that, the private key never leaves the device, and that's the importance of securing it inside of a closed, secure, tamper-resistant system. And then from there, the public keys are what are used to for signatures, for certificates. So it's, again, that relationship between the private key and the public key. The public key has information to prove that once that private key is been validated, that public key can be used for the certificates.
Great. My next question was, how can you protect edge devices that don't have the same computing power as enterprise servers?
Yeah, that's the it's kind of the crux of the IoT security question, which is servers are used to software-based or hardware-based security solutions that are centralized. So they're relying on high compute power. So you're talking about Intel class server processors and lots of computational power there. And then you get down to, like my example, a bathroom scale. It doesn't have the same computational power. The good news is that the cryptographic standards that are used in this public key infrastructure is actually very manageable for a connected device to perform the functions that are required of it, because it's creating the connectivity from one point. It doesn't have to do thousands of transactions up in the IT infrastructure. So the computational power, even all the way down to sensors, so just even a thermostat inside of a, say, a smart factory, has plenty of computational power to be able to perform the cryptographic functions connecting to a secure element to create the highest level of bank and government grade security for that connected device. So it's just a matter of the entire infrastructure and ecosystem building and demanding that that device has an immutable identity and then uses cryptographic standards to protect itself through the network.
Great. And why is the root CA trusted in the first place?
Yeah, so trust isn't built overnight. I know it sounds cliche, but it's built over time. So it's built over time where you have been trusted to secure identities, to secure individuals, to secure organizations. So it takes a long time for people to recognize a root of trust. So it's not something you can just start up today and now say, I have the trust built up in my root certificate authority. It takes time for that to be established. And in addition to the time, it takes certifications. So you have to be certified by standards and bodies that recognize you have put the correct security procedures in place, your facilities have been inspected, and now we can trust that you have the authority to create this root key that has never been exposed, will never be exposed, and we can trust you to protect that in the appropriate manners. So it takes, the root CAs are trusted because of the time they've invested to build that trust and the certifications that they go through in order to create that.
Thanks, James. And one other question we received was, can we get this slide shared after the presentation?
Yeah, absolutely. I'll work with the CTA to button this up and make sure that it's available on the CTA websites.
Great, thank you. We can maybe give it another minute to see if there's any other questions. Again, feel free to use the chat box. Otherwise, James, we'll kick it over to you again.
Yeah, I realized that in keeping this kind of high level, I've given everybody maybe 15 minutes back out of their day if they scheduled 1 hour for this. So without any other questions, I would just like to say thank you to the Cybersecurity Tech Accord for giving us this platform to have these types of conversations. WiseKey is very happy to be a signatory and engaged and involved in these conversations that are happening. The ultimate message of the CTA, along with WiseKey, is that it's not one company that solves IoT security. It's the entire landscape of companies, from the edge devices, through the networking equipment, through the platforms and the applications. It takes everybody being involved with the primary goal here of protecting the users of these connected devices. And unless any other questions pop up, I think we can wrap it up.
Great, thank you so much, James.
Thanks, Michelle.